Okay, I have to go kind of like just after 6 today, so I'm going to start on time, and hopefully the people who are late won't be too disruptive. So I'm going to go through some of the questions that people had trouble with on the past 2 online homeworks, and then review some of the things with regression that we've been getting asked about, kind of. And I might not have time to get to bias variance, but hopefully the slides should be readable. So if we don't get there, you can look at them for reference. So online homework 3, I'm just going to go through the questions that a lot of people got wrong on the first try. So in a function space with this inner product derived from this kernel, what are x and y? Does anyone want to tell me if you remember, or if you do the question again, it's okay. No one? Okay. So what I'm looking at, I'm defining this inner product over a function space, right? So the elements that I'm passing to my inner product are members of this function space, right? I'm defining this thing. And I think a lot of people got this wrong and said it was elements of the example space, because when you see x and y, you usually think of them as examples, and you think of functions as like f and g or something. I think that was like a notational confusion. But does it make sense that if I'm saying I'm defining this over a function space, my elements are going to be, my input to the product is going to be functions? Feel free to stop me and ask. Like, the purpose of going over these is so you guys understand them. Okay? Yes?
So could you go over the definition of function space?
It's the set of functions that go from E to R. And you can use the word space because you can think of functions as vectors, as Jeff described in class. So if the word space is what's confusing, it's just because functions and vectors, we kind of go between them. But in this case, we're looking at a space of functions, a set of functions. So whatever I draw out of this space is going to be a function. And I can define an inner product between 2 functions.
So like, just to kind of clarify, like what we usually see is like phi of x, phi of y.
Yeah, exactly. So it's like it's the purpose of this question was to get you to do more than pattern match when it comes to these inner products. Okay, so this is another thing. I think that some people probably have not seen this notation before. Right? So what this is just the set of all kernels defined over this example space. And importantly, this set does not include linear combinations of kernels, which is what you would need to make the answer to this question true. Right? So when we use a kernelized classification algorithm, what we're getting is a linear combination of kernels as our decision rule. So I think that was the issue here. Correct me if I'm wrong. Did people feel like there was another issue?
So if it does not include linear combinations, then you should not be calling it a space.
Okay, you can take that up with Jeff.
You can have spaces without linear combinations.
This is.
No, the space in general is more abstract mathematical concept. It doesn't necessarily have to have.
Right, like it doesn't have to be closed under any operations either. Right? You can just have a space, and it can be just kind of a poorly defined.
Okay, I think everyone just thought they meant vector space.
Right, yeah, okay. So when a space is defined, like this is like set notation, right? So this is just like the set. If it's easier to use the word set for you to think about it, then yeah, whenever you see this, it's like the set of all kernels, okay? But yeah, that's a good point of confusion. I'll bring that up with Jeff. Okay, so if I define a kernel matrix, like the gram matrix for this, can someone tell me anything about that matrix based on this definition? Anyone? I thought I saw motion over there. No? Okay. Yeah, it's positive semi-definite, right? And so that's why you can kind of, that's why you know that this is a proper kernel, right? Is because the gram matrix defined from this kernel is going to be positive semi-definite. Okay, yeah?
What is E in all of these frames?
E is an example space, so E could be like R2, right? Or E could be some like set of discrete points that you're drawing from. Because we do machine learning over things that are not just vectors of numbers, we use example space to generally mean anything that you want to operate over. So in this case, X and Y are elements of the example space, right? Going back to that like first question. And I think, yeah. Is that okay? Okay. So this is like kind of a subtle point, and I can see why people got this question wrong. What would be required in order for this to be true? What would I have to change?
Can't the length be infinite?
So, okay, so that's the subtlety, right? Is that typically when someone says RD, they mean a finite dimensional vector space. And you could be like, oh, well, D could be infinity, but ubiquitously, it's never infinity when people define it this way, right? We have other ways of describing infinite dimensional spaces. So, but you're right, the range needs to be a Hilbert space. It can't just be like a, finite dimensional vector space in order for this to be true. Okay. So then this one, I guess, do people realize that the margin from perceptron is the same as the margin in SVMs? Because I think that's what, that was the connection that you needed to make to answer this question correctly. But if there was something else that confused people, please do let me know. But does that sound reasonable? I'm seeing some confused faces. No? Okay. Gonna keep going then because we have a lot to do. Okay, so this is like a key kind of idea. What does it mean for the use of something to be justified, right? So we don't actually know what the noise in the label is ever, right? And we just try and fit a model that we think might do well. So anytime that we're going to try and minimize a squared error fit to Y, regression is justified, right? It's a reasonable thing to do. Yeah?
Yeah, in the class lecture, one girl asked a question on that, and she said that it didn't have to be Gaussian, right?
Pardon?
In the lecture, she said it didn't have to be Gaussian after.
Right, that's right. So it's just that like the solution that we find just happens to be the MLE if you assume Gaussian, but it's not like that solution is like a crazy thing. So, okay, do people feel okay about this? It's just like you can pretty much always use regression. Okay, so this thing, I think people kind of had it backwards in their minds. So let's say I have this set of points. What would it look like if I tried to estimate this density using a small bandwidth kernel? Does anyone? It would fit, would it fit well or poorly? It would fit well, right? Yeah, so it would look like this. And for a large bandwidth, it would look kind of gross, right? Not like icky gross, but you know what I mean, imprecise. So with that intuition, it's clear to see how bandwidth is kind of, let me make sure I use the right word. Is it increased bandwidth, bias? Yeah, bandwidth is kind of proportional to bias, right? The bigger the bandwidth, the less precise an estimate we're getting of the underlying density. And then in the case of kernelized anything, right? Kernelized anything, you can just think of it as like a blurrier kernel, right? And so you're going to have a more biased, a more simple estimate. Do people feel okay about that? Okay, great. So this one, I don't know what the thing is. So here's what our estimator is. Our estimator is f of x is x beta, right? And then recall that in ridge regression, we get this beta hat. So at the very end of this multiplication is y, right, which are our training labels. And you can think of it, f of x, as like a big, complicated matrix times y, which, because it's weights, it forms this, when you think of how matrix multiplication is, it's like this series of inner products. So you're getting a weighted sum over the labels. If someone feels like there was some other confusion with this question, please do stop me, because I'm just going based on why I think people got it wrong. Don't actually know why. OK, and so this one, I think this was just like a reading issue, right? Right? Like you were reading it kind of quickly and then didn't realize that that said labels and not data at the end. In polynomial regression, we'll do a nonlinear transformation of the data. The labels, it's still going to be kind of like in this case, it's still going to be a linear transformation of the labels in the end. OK. So this, I think this will be more understandable later in the recitation when I cover Gaussian priors. But when we talk about, when we think about our estimator as a draw from a Gaussian process, having a diagonal covariance on that estimator tells me that I know how points relate to themselves, but I don't really know how they relate to, or they don't relate to each other at all. And when in regression, we're not going to be able to see every point in our input space because it's continuous, right? We're only going to get a sampling of points. And what we want to know is how the points we have relate to points we've potentially never seen. So when we have a diagonal covariance matrix, we don't have that information, and then we can't possibly do a regression. And you'll see, like more in the math sense, like the weight matrix we estimate is going to go to 0 if we have a diagonal covariance matrix for the Gaussian process. OK? So let's just do a quick review of regression. Do people feel OK about that, actually? All the online homework questions? OK. So let's do a quick review of regression. Remember that what we're trying to do is minimize the squared error over a set of functions to these labels y from our input space x. And these are linear functions, so the form f of x is x beta. And we can solve this and get this nice little closed form result for our weight matrix. Remember that it's kind of import to us is whether or not this quantity is invertible. And as someone has probably caused the confusion on the online homework, this result that I just showed you is technically the MLE if I assumed Gaussian noise, so that y is drawn from a Gaussian with mean x beta and variance sigma squared I. So if we maximize the log likelihood of the data under this model, we would get the previous solution. OK, so sorry. The set F here is still kind of big, right? There's many, many lines we could draw through our data. And so maybe what we want to do is kind of bias these lines to be flatter, less complex, right? So the way we do that in terms of like a probability way of thinking about things is we put a prior on the weights, that they're drawn from some zero mean distribution, in this case Gaussian. And this results, flipping it to the optimization interpretation of things, this results in a penalty. And in the case of ridge regression, oops, that's not what I wanted to do at all. Hold on a sec. I accidentally hit end instead of next arrow. OK. So in the case of ridge regression, we can get this closed form solution. And I think, is it clear how we can get this solution from solving the above equation? I mean, if you want, I can walk through something on the board. So yeah, if at any time 2 math steps don't make sense, I'll walk through them on the board if you ask. OK, don't be shy. And then the lasso, which came up. Did I see a hand? No, I didn't. OK. The lasso, which, as you know, came up on the midterm, et cetera, is a Laplace prior. Independent Laplace priors on each of the weights. Yeah?
Yeah, and I remember someone asked why the decimal of x plus x plus the lambda of I, we increase the eigenvector so that we
I see. So we're adding positive elements, right? to the diagonal of x transpose x, and if the and that'll make it the result positive. That's just like a linear algebra fact. Like that's just how we. I mean, if lambda is sufficiently large, right? Like what you want is lambda sufficiently large to make the diagonal elements positive. Does that make sense? Okay. I was not prepared to go over that particular result today. Okay. So, right, lasso. That's a Laplace prior on your weights, which results in this penalty, which the one norm is the sum of absolute values. And this isn't smooth, so you can't solve it. You can't solve it in closed form, and you can't even solve it with vanilla gradient descent, right? Because its gradient is discontinuous. So we have a special way of dealing with that that's kind of beyond the scope of this course. But you should know what lasso is. Some of you do. A lot of you do, based on your midterms. Anyway, so this is a plot that maybe gives some of you PTSD. What these plots mean, right? When we show you these to give you intuition for how a regularization penalty works, what we are looking at right now, these are the level sets of the objective function without the penalty, right? And we're looking for where they intersect the place that the norm is less than lambda. So this ball is of radius lambda. And I think it might be easier, or it might confuse you, to think about this in like 3D space. So our likelihood function is some big parabola, right? Hopefully, if it's convex, right? And then the norm is kind of like this ball. And what we want to see is just where does our unpenalized likelihood function reach the point that the weights are sufficiently small for our prior that we used, right? For our lambda that we used. So you'll typically pick lambda through cross-validation, and that'll define how big this ball is. And it will hopefully get you something that generalizes well, right? Because cross-validation is how we guesstimate test error in machine learning. So do these plots make sense to people? Like, does the intuition behind them make sense? Because I know they get thrown up a lot, and there were some interesting, sorry.
What's the definition of regularization?
The definition of regularization.
Is that just the Gaussian prior?
No, that would be the ridge penalty, right? Regularization is the idea of adding external penalties to your objective so that you bias your function to be simpler. That's what regularization means. And how you do that, with the particular flavor that you use of that is not like part of intrinsic to the definition of regularization. So both the lasso and the ridge penalty are forms of regularization. Is that clear? Okay. Okay. So let's talk about nonlinear regression. Remember we defined this A matrix, which has all the transforms of all the functions we want to worry about, like maybe this is some polynomial function. And we have our x, which is just a vector of the same function applied to our data. And recall that we can actually do nonlinear regression simply by swapping in A for where x was before, right? It's a very nice generalization, and it makes a lot of complex things possible. And actually, we can go even further, right, and make regression more expressive by noticing the following. So if A is an n by p matrix, right, what we have is in this term is something p by p plus a p by p identity, right? I got asked a lot of questions about this derivation, so I'm just going to go through it a little bit. Okay, so let's just look at this quantity right here and distribute this right multiplication of the A transpose, right? So now we have this multiplication. And notice that I can put an identity of size n here because multiplying by 1 doesn't do any harm, right? And this A transpose is p by n. Okay? So I think Artie skipped this step in class, and I got a lot of questions about it at my office hour. Yeah? Did you raise your hand? Did you raise your hand just now? Okay. Okay, so now what we're going to do is pull the other A transpose out from the left. And now we've got this, right? So the nice thing about this is that what's in the parentheses is n by n. And a lot of the time, sadly, n is a lot smaller than p. So now we have a much smaller problem. And to show what beta hat would be in this situation is that we take this end and this end and left multiply both of them by this inverse, and then we right multiply by that other inverse, and now what we have is a new expression for beta hat that involves only inverting this n by n matrix, which is swell computationally. And it's also cool. Do people feel good about this? Like how we got here? Okay. So what's also cool is that we think of, what's also cool is that this can be further generalized. So we have our beta hat that we just solved for, and then we also have our full prediction, which is just x times the beta hat. So in class, this was presented kind of without proof. But we can think of this as this kernelized thing times the training labels, where we define this kernel as being the phi x's times the phi xi's, and the other guy being the cross terms. So what we're doing is I'm just subbing this beta hat in here and realizing that given the way we defined a and x earlier for nonlinear regression, these are actually kernel functions. And these inner products that these matrices are describing could be replaced by any kernel approximation of that inner product. Are we OK with that? OK. So why is that? How does that relate kind of to Gaussian processes? So this solution we're going to show is the estimate for the assumption that f is drawn from a Gaussian process. What does that mean, right? That's kind of a freaky term. It means that I have this set of functions, for lack of a better word, and I'm going to draw f out of it, and I know that f has this cool property. If I take any 2 points on f, I know what their covariance is, what their relationship is. It's described to me by the covariance of the stochastic process. OK? And given that this is an inner product between 2 points that's characterizing this covariance, I can replace it with a kernel. Yes?
What's the size of the covariance matrix here?
That depends on f and the space that f operates over. So it can be, that's a good question. I'm going to think about how to precisely answer that. OK?
The size of the number, the more you're drawing numbers, the larger the size of the matrix is, given the definition of sigma.
Well, yeah, so it's like, does f operate over an infinite dimensional space? Then this could be infinite, right? This matrix.
It's more like you have discretized f at some points xi and then noted the covariance between 2 and xi.
Well, that's how I'm explaining how you interpret a draw from the process, right? But I could potentially draw any function. F is defined throughout its entire domain, right? So if it's continuous, then it's defined everywhere, and every point has that property, in which case it's an infinite covariance, right? So yeah, there's nothing to say that f is a discrete function. OK, it's just easier to talk about just picking 2 points. OK, so right, so our y is drawn from this kind of Gaussian, right? And so is f. F is drawn from like a weird kind of Gaussian. And so together they're jointly normal. And the important result kind of for showing that kernelized regression is the solution to a Gaussian process map is using our knowledge of what it means to have a conditional probability in a joint multivariate normal. And that result is kind of involved and potentially unnecessary. So I'm going to refer you to this proof of it, okay? So, which, I mean, we could go through slowly. I could get it up on the projector. We could go through slowly if you feel like you really want to know it. But it's kind of just like what is f of x given y? Well, you do a bunch of stuff, and you get this answer.
What is sigma and n? I never.
Right, okay. Yeah, that's a good point. Okay, so let's describe this covariance matrix. So we have n data points that y is describing. Good point, I should have discussed this. We have n data points that y captures, right? And we can pick those n data points out of f, right? We know which ones of f correspond to it. So we can just kind of block diagonalize the covariance matrix of f so that those n data points are like kind of separated from the other guys, right? So when I have this sigma nn and these xn's and nx's, what they are describing is the covariance as it relates to the particular n points that y describes. Does that make sense? So I'm just arranging it so that you can see where, because like they're jointly normal, but they're only kind of, it only matters that they're jointly normal where y is defined, right? So
these endpoints are training data.
yes, exactly. So these endpoints would be your training data.
X, Y is your test data.
Yes. Well, X could be your test data, or X is just any data that you would put in. That's right. So if we frame this like a problem, like a classification problem, you find F, and then you would sub in some X, right? So, oh, sorry.
What does jointly normal mean?
So if I have two dimensions, right, that I'm thinking about, something's jointly normal in both dimensions if it's Gaussian in both directions, right? So I have like, instead of just a Gaussian flat Gaussian along this dimension and one along this dimension, they together make this Gaussian bump with the same kind of tail behavior. So the idea is that if you look at both y and f of x together, they form a kind of Gaussian that can be described by this covariance. Mm-hmm.
What about the top right one?
The top right, so it's going to, it's 4 squares, right? But it's hard for me to tell you what the second, well.
In general, the diagonal matrix can be rectangular.
Right.
So like the top left is going to be n by n. And let's say the other one, you have k points in x, right? So the top right would be n by k. Bottom left would be k by n.
Right. They just have to add up to a square. So
Every training point.
crossed with every test point. If you want to think of it the way he described as x being your test points. So sigma nx is just like there's n training points and k test points, kind of like Abu was just saying. Yeah. So all I've done really is just parcel the covariance matrix in a convenient way. Okay?
If you have like n-dimensional data, if each dimension is a function, can you guarantee like the joint distribution is also a function?
Can I guarantee that this is a Gaussian?
And in general, right?
In general, if I have n data points that are each drawn from different Gaussians.
I mean,
are they together jointly Gaussian? So the reason that these are together jointly Gaussian is because y equals f plus epsilon. Right? There has to be a relationship. Like like two Gaussian variables are not necessarily both like jointly Gaussian, right? It's because y is kind of drawn from a Gaussian with mean f and variance sigma that you get this kind of relationship. Was that your question?
I mean, like, if you have like n features and each feature is a Gaussian, so independently each feature is a Gaussian. So does that mean like the whole features are essentially from a joint Gaussian distribution?
No.
If they're independent, then yes, but if you have dependencies, like in this case, they're not necessarily.
Yeah, not in general, no. Okay, now I understand what you were asking. Yeah, okay. So, right, okay, so we do some stuff, and we know that f of x given y is drawn from this distribution with this mean, which should already look familiar, right? It looks exactly like the kernel result that we got just from doing matrix stuff on our original result. Okay, so the thing with Gaussian processes that is important to remember is that you're drawing a function that's described by some covariance over its domain. And your result, if you assume that your regression function is a Gaussian process, you'll wind up with the same result we get when we just kernelize nonlinear regression. Okay, I think those are like the kind of important points. Boo, if you want to add anything. Okay, great. Okay, good. So let's talk about the bias-variance trade-off. I got some points. We're going to talk polynomial curve fitting at first, and then we're going to talk a little bit more about classification. So, okay, so how can I fit these points with a polynomial? The simplest thing I could do, right, is just a constant. That's pretty bad, right? Or I could do a line. That's a little bit better. Or I could do something really high order, right, like a 9th order polynomial or something. So in these cases, I haven't really fit my training data super well. And so we would say that the bias is high, right? Because how well I'm doing on my training data is limited by how complex my model is. And so for simple models, you generally have high bias. For a complex model like this that fits my training data perfectly, I'm going to have no bias at all, right? Because I pass through all of the points. So, you know, as you think of complexity increasing, bias is always going to go down. Oh, this is not how that was supposed to go. OK, so if I take a data point out of my training set and then I retrain my regression, right, my fit, how much is my model going to change? Well, in the constant case, it doesn't really change at all. And in the linear case, it changes like a little bit. But in the high order polynomial case, it changes a ton, right? And so this like amount that a function changes as you manipulate the training set gives you an estimate of the variance. So in this case, right, and so when we think about our error on some like previously unseen training set, we care about both of those quantities, right? So the constant function is like pretty much never going to do well. It doesn't have much variance, but it has really high bias. It doesn't fit my data well. The line is kind of a sweet spot, right? Like it's got, you know, non-zero bias, but it also has kind of low variance. Whereas this guy is going to be like a huge problem, right, for a test point. Like if I put back that point that I took in, it's like all the way up here, I'm going to make like a huge mistake there, right? So do people feel comfortable with like as complexity increases, bias goes down, variance goes up generally because you're fitting better, right? So taking away a data point is going to impact your model more. Okay. So how do they relate to the functions we learned, right? Like we talked a lot in regression about learning these functions f. So if we think about like the class of functions that we're learning, so this would be like the set of all linear functions, right? There's some true function, and it's probably not a line, right? My data, for example, a word that you're thinking about is not a linear combination of your brain activity at a bunch of locations. That's like a ridiculous idea that that's the truth. So there's some true function that generated your data, and you don't know what it is, but we're going to try and fit a line to it anyway, right? Or something else. You have a class of functions you picked. And then within that class of functions, you don't see all the training data you could ever possibly see. You have some finite subset of possible training data points. And those kind of put you in like this little section, right? Maybe the training data are distributed such that I will never learn a line that goes like this. I'm only probably ever going to learn lines that go like that. Something like that, right? So if I had infinite training data, then this is probably the best function I could ever hope to learn, right? It's the closest I could possibly get within these two balls to my true function. And the distance between that guy and the true function, that's our bias. So in the case of the polynomial fitting example, this constant flat polynomial is really far from the true function, which was probably a line of some kind, right? Not flat line. So it's got high bias. So the idea is like, even if we learned the best constant guess for the data set with infinite points, it would still not fit. But how much the model changes in this space, right? Like the difference between a function kind of on like this best function and maybe the worst function we could possibly learn, that's going to be the variance. So how much do we move around in this little ball? And because we have finite data, the variance really matters, right? Because we're only seeing a small subset. We don't want to overfit to the subset we have. So when we think about overfitting or underfitting, bias is kind of like how much am I underfitting, and variance is how much am I overfitting to my training data. Okay, and then the function we actually learn is based on some portion of the training data space, right? And so it would be something like this. And so then the error that this function has is kind of characterized both by its distance to the edge of the red circle, which is captured by the variance, and its distance from the red circle to the green one, right? So do people feel comfortable with this concept? Because this is pretty important. You get people in kind of all fields of science generating these models that overfit and being confused about them. So kind of important to understand this. Okay? No questions? Okay, great. Then we got through everything that we needed to get through, and I can stay like a little bit more if people want to ask me about some other stuff.
I got a previous question about the rich regression and the lasso. We got a very good picture about the 3D.
This thing.
Yeah, I wonder what is the picture like for lasso case?
For the lasso, it's a diamond. It would be kind of like, can you see this board? Oh, okay. It's not obvious to me. Okay, so here's my axes kind of. Oh, this is going to look like terrible. And the idea behind the lasso is that we have kind of a diamond shape, right? Because it's an absolute value function. It's the sum of absolute values along each dimension independently, right? So in the case of this, it's just absolute value beta 1 plus absolute value beta 2. Okay? And so our L1 norm ball is going to look like this point. And you can kind of see why it encourages sparsity, right? Because it peaks out the most, it's the biggest, where only one dimension is positive. and the other one is set to 0, right? So like along here and along here. And so when I'm touching it with my likelihood function, I'm probably going to run into it somewhere where only one of the weights is active. Is that good? Okay, cool.
So I think like I understand the general like what this is trying to do and everything, but I guess so you're making two equations for both the things you're adding for the minimization, and then what I don't get is so you've got like the circle is generated from the beta when we're in the not the lasso and we're in the
We're in the ridge case. This guy, yeah.
And so then you've got lambda, which changes the size of the circle.
Mm-hmm.
But that's assuming you're setting it like equal to something on the other side. Are you setting it equal to 1? Or?
So you pick, so the way that you would run ridge regression is that you would take your training data. Let's think of like the least computationally expensive thing. You would take your training data and you'd set aside like 10% of it. And then you would try like every lambda in a really wide range. And you would get a beta for every lambda. And then you would see how well does this beta work on that 10% that I held out. Does that make sense?
Oh, you're talking about cross-validation to find the
Well, I mean, that's just holding it out. I'm not cross-validating. If I iterated that 10%, then I would be cross-validating. But yeah, so what I'm saying is that lambda is something that is what we would call a hyperparameter, right? Beta is a parameter you learn from the data. Lambda is something you have to choose in kind of a rigorous way. And so we do it that way.
I guess I was more asking, like, since you're making two equations from this, from the two things added, you need two equalities. So what is the
what do you mean by two equalities?
Like to make the two equations, you need to set the beta part equal to something with the lambda. So like lambda times the beta squared equals something. To make like a circle, you need an actual equation. You can't just.
Oh yeah, sorry. That's beta. That's norm 2 of beta less than lambda. That's what that is.
So it is 1. It's like
So, well, I mean, if I, no, it's less than 1 in this picture, right?
Yeah.
It's just some number.
Okay.
I just tried this lambda, and it intersects my likelihood in this place, right? Okay, sorry, I misunderstood your question. Other questions about stuff?
Sorry, but in the case of lapsos, it's a diamond shape. So why is more likely to be the solution is more in the coordinates rather than in the middle?
Maybe I should draw this bigger. Okay, I'm gonna try putting the left display up, and hopefully it won't break anything. Okay, and then I will draw on that board. Okay, you guys don't know, but I broke a bunch of stuff before you came in. Okay, so think of it as if this wasn't like poking out, but rather was flat down, where would that level set intersect, right? It's going to intersect at the point. So is this visible to people? Okay, just holler if it's not. So I've got this, and let's say here's my level set, here's my MLE beta. Okay. So the ridge guy kind of sticks out a lot. The lasso is going to be like this. So this level set isn't going to hit my lasso, even if it hits my ridge. What I need to do is go further from the MLE, right? That's a terrible drawing, I'm sorry. But the idea is that you're going to intersect it depends on the function, but you're going to intersect this ball probably where it sticks out the most, right? So this sticks out the most at these areas. And you're never going to, like, it's so unlikely that my curve is going to be tangent to this line before it hits, like, one of its endpoints. Its endpoints are sticking out so far, right? But, like, if it's hard to visualize like this, then you can think of it also as in how do we actually solve this optimization problem? So the way that you solve kind of the lasso is that you take a gradient step, and just to, if any of you are curious, this is called Prox gradient descent. Anyway, what you do is you take a gradient step, but you understand that the gradient of this is discontinuous, right, when we're close to 0. And so what happens is after you move along the gradient, you check and see if beta I is less than lambda, then it goes to 0, right? And so the lasso, because we optimize it in this way and it has this kind of sharpness, right, in its gradient, you wind up with absolute zeros in it. So there's like two ways you can think about it, right? Is like these two objectives intersecting, which if you don't buy that geometric argument, I don't blame you. It's like hard to visualize. Or you can just think like, when I solve this function, when I like travel to the minimum of this function, I'm gonna need to set some betas to 0 to like make that happen. Okay, sorry, I hope that didn't like confuse you. This is kind of beyond the scope of the course, how you solve the lasso. No, it's proximal gradient descent. You can't use gradient descent because the derivative of absolute value is not defined at 0. It can be, in fact, the derivative, well, it's not a single point at 0, right? So here it's 1, here it's -1, but then at 0, it could be anything in the range of -1 to 1. And so what we do is that we do this kind of soft thresholding. If the absolute value of beta is greater than lambda, we leave it alone. And if it's less than, we set it to 0. Okay, but this is not something that you guys like, you're never going to be like tested on this in this class. Okay, are there other questions about stuff? Because yeah. We moved kind of quickly. Don't be shy.
Do you think doing the lasso optimization is doable in our projects? Like, are there a lot of
Yeah, definitely.
Okay.
Easily. Don't use MATLAB's implementation. Please find a different one. Or write it yourself. It's not very hard. And if you like meet with your TA, who's your mentor, they can easily explain it to you. But it's never going to be like on a midterm or anything. Other questions?
So
Yeah.
for the Gaussian process, do you draw a function or do you draw the points from that process?
You draw a function.
So
And you pick, so you draw a function, but those points that you referred to as our test points are where you evaluate the function. So you don't evaluate, right? So what I work with for the rest of this demonstration is the function I drew evaluated at a particular set of points. So in that, does that make sense? So
with any function, it follows the same sigma.
right. Any function I draw from here is going to follow this sigma. And I just care about evaluating that function at my test data, for example, my test points, or my training points, like wherever.
Is there an expression for that sigma?
Or you choose it usually.
You pick it to be,
Higher kernel, correct.
right, so when you pick the kernel, you're kind of defining the Gaussian process you're drawing your functions from. You're saying, I want functions for whom the covariance is defined by this inner product.
It's the same as SVM, kernelized regression.
In the regression part, there was some tricks to do. You started from a P by P matrix.
Yeah, here, this one.
Yeah. So I think you start from a P by P matrix and end with an N by N matrix.
Well, so I don't really, right? So what I start with is a P by P times a P by N, right? Like, so this guy in the parens is P by P, but the A transpose is P by N. So I'm always going to have a P by N matrix when I'm done.
Of course, I was
That's right.
But in that case, what is the advantage of that? You said P by P is always larger than N.
In like real life data sets, P is larger than N.
It will make much sense because we have a lot of more features to learn than
Yeah, so P is the number of features, right? P is the number of features and N is the number of data points.
Yeah.
So typically I have, for example, 20,000 voxels, but only 8 participants.
Yeah.
So it's like a huge order. I'm sorry, I don't understand your question.
I think we have a limited number of training points. How can we define a large number of features, which is?
Oh, you're saying, am I losing information?
Yeah.
Oh, okay. Well, I still have to compute this inner product, right? So I'm not like, it's not like that information goes away. It goes into this inner product.
I think the question is, we have defined a large amount of features, but we only have a limited size of training points.
Uh-huh.
I think it really makes sense because we have limited training points and we have a large amount of features, which is much larger than the number of
So what doesn't make sense?
So it's like, for example, if you want to learn like 200 features, but you only have 20 data points, and will that really be a reasonable machine learning model because you have?
So that's the motivation behind regularizing, right? So if I have many, many features and a few data points, it's super easy to overfit. Right? That's the phenomenon you're describing because the variance is so high, right? There's so many dimensions on which I can mess up. So that's why we regularize, and that's why, and you'll see it in the math. If P is much greater than N, then this matrix, this A transpose is going to be, it's like super low rank, right? All of these inner product matrices wind up being very low rank, and so they're not invertible, they're badly conditioned, and typically lambda needs to be very large. The more features you have, typically the bigger lambda is going to be. Does that answer your question? Okay. Other stuff? Anything? Anything at all? Okay. Well, I'll see you guys later then.